Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think yesterday we were discussing about the synthetic application of ethyl acetoacetate or acetoacetic ester or beta keto ester. One application we have seen, we have synthesized the target molecule 2-butanone using ethyl acetoacetate. Today we are going to discuss remaining now the second application, that is the synthesis of 2-pentanone 2-pentanone using ethyl acetoacetate or acetoacetic ester, or we can call it beta keto ester. So we are discussing chapter number 2, that is active methylene compound. What do you mean by the active methylene compound? According to the definition, the CH2 group which is located between two strong electron withdrawing group, such CH2 group are known as active methylene group or reactive methylene group, and those compounds containing such group are termed as active methylene compound or the reactive methylene compound. And as far as the TYBSc concerned, I am repeating these sentence again and again. Only two molecules we are going to discuss in this chapter. One which we are presently discussing, that is the ethyl acetoacetate, which is prepared by using one named reaction, that is a Claisen ester condensation. And as we know that Claisen, how he prepared that or synthesized that compound, he has taken as a starting material as a 2 molecules of ethyl acetate treated with the sodium ethoxide, and the resulting compound formed will be the beta keto ester, or we can call it as the acetoacetic ester or the ethyl acetoacetate. And now here if you see this second application, synthesis of 2-pentanone using ethyl acetoacetate, or from, you can use the word using or from ethyl acetoacetate or acetoacetic ester. While solving such kind of the example, what you need, what you require the planning. First you plan how you can prepare this molecule in the laboratory. So here, see here what you need. Here you must know the structure of 2-butanone, then and then you can able to synthesize that molecule. For that purpose we require to know the structure of 2-pentanone. Remember here, pent indicators, there are 5 carbon atom containing in this molecule. So we can write the 5 molecule this way. And as we know that here 2 indicate as a position of some functional group. Which functional group is here? Look at the last suffix is ONE. It means that ketonic group is present, carbonyl group is present. The carbonyl group is present in this compound at which position? At 2 position. You can give the number either from left hand side or right hand side. So I am giving number from the right hand side 1, 2, 3, 4, 5. See carefully at 2 position. Here there is a carbonyl group. To indicate the position of that carbonyl group, and that's it. Now the remaining, as I already told you that if only one bond is there, how much hydrogen to attach? 3 hydrogen. Terminal carbon should carry 3 hydrogen atom, and this middle one, it can carry CH2. Here 2 bond is there, so you can attach 2 hydrogen atom, and here you can attach CH3. So this is the structure of 2 pentanone. Once you draw this structure, let me make this structure like this for sake of convenience. Now is what needed? Planning. Remember, in the planning, I am marking here, highlighting this part of this molecule, CH double bond O CH3. Here in the first point, you can say CH double bond O CH3. CH double bond O CH3. This part of the molecule, this part of the molecule, this part is coming from, you can write in short, this part of the molecule or the compound is coming from ethyl acetoacetate or acetoacetic ester. And second point, look at here. Once again I am marking this, I am putting this in the square bracket. This is our TM, we can call it TM, means target molecule. And as I already told you in my previous lecture, TM means target molecule whose synthesis being planned is called as a target molecule. So let's see here, this part means this CH2 CH3, that ethyl part, this part is coming from this part of the molecule or you can say compound molecule is coming from primary alkyl halide. See here, we know that alkyl halide, the organic compound having a general formula Rx, is known as alkyl halide, and that alkyl halide broadly classified into 2 types: primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. So likewise, but here these 2 points is required. Now is the synthesis. Next point is the synthesis. First we planned here, now the second point will be the synthesis. Now in the synthesis, they have given us target molecule as well as they provided us the starting material also, and you have to go sequentially or step by step to get the final product or the target molecule. So there are certain steps are there, certain processes are there, and by doing such process you will arrive at your end designation, means you can achieve your target molecule. by using that. So let's see here. You know the structure of ethyl acetoacetate will be this one, CH3, C double bond O, then CH2, then C double bond O, OET. It will be the structure of acetoacetic ester or ethyl acetoacetate, which containing as a reactive methylene group, means this CH2 group is a reactive methylene group or active methylene group, because the methylene group which possess two proton which is highly acidic in nature, and therefore by using as a base or base catalyzed reaction, it can abstract the more acidic proton and form as a carbanion, and the resulting carbanion is well stabilized due to the resonance, and therefore it is important one. Now the first step we can use as a base here, NaOET, is known as sodium ethoxide, and sodium ethoxide, what it will do, it will abstract the highly acidic proton. You will get CH3, then C double bond O, then CH minus, C double bond O, OET. Here you can write minus and Na plus. So let's see the next. I am clearing this part over here so that you can see clearly. I am writing this structure once again here, or from this structure I am putting here. So let me draw once again this structure. CH3, C double bond O, CH minus, then C double bond O, OET. This is known as acetoacetic ester, or is a carbanion formation. Now there we can use this one, CH3, CH2 and Br, which is ethyl bromide, and that process is known as a alkylation. This process is termed as monoalkylation. So here there are two carbon atom. Out of that two carbon atom, which is a more electrophilic in nature, because here the intermediate which is a carbanion and which is act as a nucleophile. So there is a nucleophilic substitution reaction. So here there are two carbon atoms are there. What do you think, which one is a more electronegative in nature? Either this CH2 or CH3? Yes, this CH2 is a more electropositive in nature, electron deficient center, because there is a bromine atom. Bromine atom, as you know that it is a more electronegative atom than the carbon atom, and therefore the electron density goes away from this carbon atom, and it shows it possesses the electrophilic nature, means partial positive charge on that carbon atom, and that Br has partial negative charge, and therefore preferentially or exclusively this negative charge is attacking on that CH2. There is a departure of that Br, and you will get here CH3, then C double bond O, CH. I am writing here this CH2 and CH3 ethyl group this way, then C double bond O, then OET. That's it. Now, due to the lack of space, the limitation of that blackboard, I am once again cleaning this, removing this other part, you know that. So Let's see here. After the alkylation, one process we can do here, that is known as here H2O in presence of H plus. This process is known as a hydrolysis. This is known as a hydrolysis. What do you mean by hydrolysis? Means what? The ester group is converted into acid. That process is known as a hydrolysis. There is a ester group, so you will get here CH3, C double bond O, then CH, then CH2, here CH2, CH3, C double bond O, then OH, like this. And now after getting that beta keto acid, there is a one process, just heat it, and after the heating there is a elimination of carbon dioxide, and it is also as a one of the process, and that process is known as decarboxylation. That process is known as a decarboxylation. And after the decarboxylation, how this carbon dioxide get evolved? Look at here, this sigma bond forming as a double bond with that oxygen atom, and this double bond retain as it is, and this sigma bond concentrating electron density on this carbon atom forming as a negative charge over there, and you will end up with the resulting compound obtained will be this one, C double bond O, now CH minus charge, then CH2 and CH3. Now this carbanion, now here another H2O in presence of H plus, you just work up, means take the appropriate amount of the crushed ice, stir, pour this reaction mixture on it, stir well, you will get the end product or the final product, and this will be CH3, C double bond O, then CH2, CH2 and CH3, and this will be your 2 pentanone, 1, 2, 3, 4 and 5. This will be your target molecule. So in this way you can prepare thousands of compound or more than that by using this strategy, and this synthetic approach is how it can be, we can prepare this one. So now let us see one more example over here, that is application number 3rd over here, and let me, so I am cleaning this one first, still wait a moment, shortly we will see the second application. Now see here, synthesis of 3-methyl 2-butanone 3-methyl 2-butanone using ethyl acetoacetate or acetoacetic ester. Now as we know that, as usual, what we need first, we require to draw the correct structure of the 3-methyl 2-butanone, which is a starting material. Everything is given, they have a given starting material as well as end product also given. You have to remember those steps. First step, we are generally using base, because this is a base catalyzed reaction and we will get that one. So let us see, but indicate as a 4 carbon atom in the straight chain like this. Now 2 position means here we can put this one. So at 3 position, if you remember here 1, 2, 3, 1, 2, 3, 4. At 3 position there will be a 1, 2, there will be a methyl group. So I am putting that one. So remaining part we can attach the appropriate number of hydrogen atom. Here only one bond is there, so you can attach 3 hydrogen atom. This carbon atom already has a 4 bond, so there is no need to attach hydrogen here. 1, 2, 3 bond is there. You attach 1 hydrogen over here, and now this carbon atom, which is also terminal, so you can write as a CH3. Now look at, this is our target molecule, and as I already told you that target molecule means whose synthesis being planned is called as a target molecule. Now I am making, this is a now planning, right? First is a planning. In the planning, CH3 C double bond O, this part I am marking over here. This part is coming from, so this one CH3, either you can write C double bond O CH. This part is coming from, this part is coming from ethyl acetoacetate or acetoacetic ester. In the second point, this, look at here, here is a one methyl group, here also has another methyl group. So here you can write this CH3 group, this part is coming from, this part is coming from primary alkyl halide, that is CH3 Br we can say. And the third point we can mention here, again look at, this is the same identical group CH3, and this part also, this part also this part also coming from primary alkyl halide, that is this one CH3 Br we can say. Br, either you can take Br or chlorine or iodine, that is depending upon your personal choice. Now is a synthesis. So now synthesis we can carry out here. Synthesis, this is the first plan, this is the second point. Synthesis, they have given the starting material here, which is this one CH3 C double bond O, then CH2 C double bond O OET, which is a acetoacetic ester or ethyl acetoacetate. And as usual, you can treat this on treatment with sodium ethoxide. Will get the formation of that carbanion, and that carbanion is well stabilized due to the resonance or the mesomeric effect. CH minus, then C double bond O ET. Look at this one, CH3 C double bond O CH minus C double bond O OET. As it now, once again I already told you that the limitation of this blackboard. So now here we have a CH3 C double bond O, CH minus, then C double bond O, OET, and now it will be treated with this one, CS3, then Br. This process is known as a alkylation, monoalkylation we can call it over here. Only one carbon atom, that nucleophilic substitution reaction takes place, and we are getting here CS3, C double bond O, then CH, CH3, then C double bond O, OET. And what is now I am once again making here the space so that we can see the remaining reaction step by step. Now here generally we have our starting material, target molecule, which is this one, CS3, C double bond O, CS3, and here CS3, right? And as usual, this is coming from the acetoacetic ester, and we should introduce two methyl group. How do you introduce? Here is the ester group. Don't do the esterification over here. Remember, here some of the student may convert that ester group into as a acid. Once that converted into as a acid, and there is a one proton which is the methylene proton and one acidic proton, which one there is a competition, which one is a highly acidic in nature. Definitely acidic proton is a highly acidic in nature, and therefore required, whatever the required expected product you won't get. And therefore here remember, the first, after the first alkylation, again treat this molecule with the base NaOET. Don't do the hydrolysis. Before that you use a base over here, and base which can abstract the highly acidic proton, that is methylene proton. You will get CS3, then C double bond O, C minus charge over here, CS3, then C double bond O, OET, right? And once the carbanion is formed, then you can treat this molecule with once again another molecule of methyl bromide. Can call it this one again, alkylation, and this is going to attack over there. Br is departure, so you will be getting here CS3, C double bond O, then C, here methyl group here, another methyl group here, and this ester group as it is. And now you can perform the next step will be the protonation. Here you can do the H2O in presence of H plus. This is known as a hydrolysis. This process is known as a hydrolysis. Hydrolysis means ester group is converted into as a acid. That process is known as a hydrolysis, and we will get here this is the product CS3, one CS3, then C double bond O, then OH. And after the hydrolysis followed by decarboxylation, just heat it. This triangle, you know that this triangle is nothing but as a heating, and you will get there is a evolution of carbon dioxide. This process is known as a decarboxylation. Decarboxylation. What is happening here? This forming as a double bond, this double bond revolving around it, retaining as it is, and negative charge is forming on this carbon atom, so that you will get here CS3, then C double bond O, then here minus charge CS3, another CS3 over there, and finally do the hydrolysis H2 in presence of H plus. This process is known as a hydrolysis, and after the hydrolysis you will get your target molecule CS3, C double bond O, then here CH, CS3 and another CS3, and this is nothing but your target molecule which we got in this way. I think this is the enough. These are the 3 applications we have seen so far. The remaining application we will discuss in our next upcoming lecture. Till then, wrap up the today's lecture. Thank you. Have a nice day.